Very good morning, students. Today we will start a new topic, electric potential energy. Yesterday we have discussed about electric equipotential surface. Now next one is electric potential energy. It is after electric potential. Now first of all we have understand what is electric potential energy. Then we will discuss about electric potential energy due to 2-point charge, then for 3-point charge, and then for n-point charges. Now what is electric potential energy? As we already know that the potential energy is equal to amount of work done. So now to derive it means the electric potential energy is also the amount of work done. But what is its definition? It is amount of work done in assembling a charges from infinity and to locate them in one particular point. That is the electric potential energy. Now with the help of the paper we will understand. Now this is the electric potential energy. Now what is electric potential energy? It is defined as the amount of work done in assembling the charges at their location by bringing them in from infinity to a given point. The amount of work has to be done, that is called electric potential energy. Actually this is equal to the work done. Now with the help of one article, that is the potential energy of a system of 2-point charges, we understand about electric potential energy. Now let us suppose there are two charges which are places at infinity, q1 and q2 in space at infinity. Now let us suppose there are 2 points, p1 and p2 are 2 points. p1 is at a distance r1 from a origin and p2 be at a distance r2 from the origin. r1 and r2 are the position vector. r1 and r2 are the position vector that which shows the position of p1 and p2, 2 points from the origin. Let us suppose p1 and p2 are at the distance between that two is r12, the distance between p1 and p2. Now to bring or assemble the charge q1 from infinity to point p1 and q2 from infinity to point p2, the work has to be done. That work done, the total work done, let us suppose to bring the charge q1 from infinity to point p1 is w1, and to bring the charge q2 from infinity to point p2 is w2. So therefore w1 plus w2, that is the total work done to bring both the charges from infinity to p1 and p2. So therefore total work done is equal to electric potential energy of 2-point charges. Now as we know, whenever to move a charge q1 from infinity to point p1, there is no charge in the space. Clear? There is no charge, therefore there is no electric field. Now as we know, work has to be done against the electric field, but initially there is no electric field in that region. Therefore to bring a charge q1 from infinity to point p1, no work has to be done, it is easily moved. Therefore w1 equal to 0. Now to bring q1 from infinity to point p1, no work has to be done, that is equal to 0, w1 0. But as we know, whenever the q1 is at a point p1, it produces electric field around it. Now to bring a charge q2 from infinity to point p2, work has to be done. What? The against the electric field produced by the charge q1. Clear? So therefore, first of all, because it produces electric field, therefore there is an electric potential at point p2 due to q1. So therefore the work done is potential into charge. So first of all we have to find the potential at point p2 due to q1. Therefore now to move a q2 from infinity to point p2, work has to be done what against the electric field or electric potential produced by the charge q1 at p2, that is r2. Therefore electric potential at q1 due to p2 at a point p2 at a distance r12 from p1 will be the potential v1, that is k q1 upon r12, k q1 upon r12, because potential is k q by r is r12 here, to r12 and charge is q1. Therefore work done to move a q2 from infinity to point p2 is w2, that is potential multiplied charge, and potential at point p2 is this one, to k q1 upon r12 into q2, so this one k q1 q2 upon r12. This is equation number 3rd, that is w2. Therefore as the work done is stored as a potential energy, therefore U equal to W1 plus W2. U is a potential and W1 plus W2. W1, the work done to move a charge Q1 from infinity to point P1, that is 0, plus W2, work done to move a charge Q2 from infinity to point P2, that is K Q1 Q2 upon R12. That is equal to K Q1 Q2 upon R12. This is equation number 4. This is all about the potential energy of a system of 2-point charges. U equal to K Q1 Q2 upon R12. Hope you understand. Thank you. Next topic, that is a potential energy of a system of 3-point charges. Potential energy of a system of 3-point charges. Earlier we discussed potential energy system of 2-point charges. Now 3-point charges. Now let us suppose there are 3 charges Q1, Q2, Q3, and all are at infinity. Now to bring a charge Q1, Q2, Q3 from infinity to point P1, P2, P3, work has to be done, and that work done is stored as a potential energy. That work done for Q1 is W1, for this one W2, for this one W3, and total is W1 plus W2 plus W3, and that total work done equal to potential energy. Now let us suppose P1, P2, P3 are 3 points. P1, P2, P3 are 3 points which are at a distance R1, R2, R3 from the origin. Now the distance between P1, P2, R12, distance between P1, P3, R13, distance between P2, P3, R23, that are distance. Now first of all, to bring a charge Q1 from infinity to point P1, work has to be done. No work has to be done because there is no electric field. Therefore again W1 equal to 0. Already discussed in the last article. Q1 from infinity to P1. Now to bring a charge Q2 from infinity to point P2, work has to be done, but against the potential produced by Q1 at point P2. So therefore work done W2, K Q1 Q2 upon R12. Directly we have to use this relation, last article relation. Now to bring a charge Q3 from infinity to point P3, work has to be done, but against the potential produced by Q1 as well as Q2. Q1 as well as Q2. Clear? Q1 as well as Q2. Therefore, because there is electric field produced at point P3 due to Q1 as well as Q2. Therefore, the work has to be done, but against the potential due to Q1 and Q2. So therefore, now to bring a Q3 from infinity to P3, work has to be done against the potential due to charges Q1 and Q2. Therefore, potential at P3 due to Q1. First of all, we have to find a potential at P3. Potential at P3 due to Q1. Then potential at point P3 due to Q2. So first of all, potential at point P3 due to Q1, V1 equal to K Q1 upon R13. R13 is the distance between P1, P3. R13, and similar potential at P3 due to Q2 is V2, that is K Q2 upon R23. This is equation number 4. Therefore, work done to move a charge Q3 from infinity to P3 is given by, that is W3 equal to potential at P3 due to Q1 and Q2, both the potential multiply charge, that is Q3. Now put the value equation 3rd and 4th. That W3 equal to K Q1 upon R13 plus K Q2 upon R23 into Q3. That is equal to K Q1 Q3 upon R13 plus Q2 upon R23, because K is common here. This is equation number 5th. This is equation number 5th. Now therefore U equal to W1 plus W2 plus W3. That is, what is W1? Equation number 1, 0. What is W2? Equation number 2, K Q1 Q2 upon R12. What is W3? Equation number 5th, K Q1 Q2, K Q1 Q3 R13 plus K Q2 Q3 upon R23. Now when we add, we get the result U equal to K common from all these, Q1 Q2 R12 plus Q1 Q3 R13 plus Q2 Q3 R23. This is all about the potential energy of a system of 3-point charges, and the relation is equation number 6, UK Q1 Q2 R12, Q1 Q3 R13, Q2 Q3 R23. Hope you understand. Thank you.